What's up, tricksters? Alan here for what is going to be a very long section. This is the start of graphing. And so with this one, there's going to be a lot of building and just kind of getting you used to this new criteria that we're going to be looking at enabling for graphs. And of course, we're going to start with the two easiest trig functions that we have, and that is sine and cosine. So get ready, because here we go. So as I mentioned to you all, this is where we're going to start graphing, which is namely the geometry part. And we're going to see how we combine the algebra that we've been talking about and evaluating all these trig functions to graph them on an x and y axis we call the rectangular. And so we're going to start by looking at the two easiest trig functions that we can evaluate, and we'll kind of talk about that unit circle and all of our reference angles or arcs that we've been talking about this far. And hopefully a lot of that is now becoming easier and just off the top of your head from all those previous sections we've been dealing with them. And again, we've been focused on those big three trig functions, sine, cosine, and tangent, but we're going to start with just sine and cosine. We'll get to the tangent and all the other reciprocal functions as we progress through, and you'll see why. They're not nearly as nice, and you guys may even know why that might be. And that's because sine and cosine, remember, are the y over r and x over r respectively. And when we get these ratios out for any angle, the nice thing about it is we have the radius in the denominator, which can never equal 0 because it's a length. And if we don't have a length, then we don't have a circle or an angle to actually build. So getting back to what we were mentioning, we're going to call that the domain or the input for the things that we can actually evaluate these trig functions, which typically is our x-axis. And if you remember that, the domain and range from algebra, the domain was all the input values, where the range was all the output values. And for us in algebra, that was typically the x's, and the output was the y values. And so the way that I remember this is D comes before R in the alphabet for domain and range. And what we're typically dealing with are X's and Y's, and X comes before Y in the alphabet. So if you line these up alphabetically according to their pairs, then you know the domain is typically all of our input values, the X's, and the range is all of our output values, the Y's. So for us, when we're dealing with trig functions, we're talking about y equals sine of some angle. And we've been using theta for degree measurement typically. We've been using s for some real number of the arc length, which we said was equivalent to theta. So now we're going to use x to also denote some angle, some input. All right. So now it's going to look more familiar for when we go to actually graph these things, and we'll talk about an x-axis and a y-axis, just like we always have since the beginning of our algebra and geometry careers. All right, so we're going to start discovering what a lot of the attributes are to this. And if you remember, one of the very first things you ever learned to graph in algebra was a line. And believe it or not, you actually started with a thing called a t-chart for the letter that it resembles. And that's when we input some values for x and we got out some value for y. Namely, the preferred form was this. We called slope-intercept form. And when they gave us something like this, y equals 3/2 x minus 5, for example, we then said that takes too long to sit there and input things that are both divisible by 2, then had to be multiplied by 3 and subtracted by 5 just to find the output. And we need to get a few of these ordered pairs in order to graph our line, whatever it looks like. We said that took too long. So we wanted to find a quicker, easier way, and what we discovered was if we know the slope and the y-intercept, then we can just graph these in order of the alphabet, b, our y-intercept, and then m, our slope. And that would give us 2 points that we'd be able to graph, and we'd be able to graph it like that. Eventually, that's what we would like to do by the end of this section, or at least after you practice it and give it some time to sink in and get used to it, just like you had to with this equation of a line. So that's our goal. And what I'm going to do is actually start you off with an example just to kind of get you used to this. And I'm going to start with a t-chart, even though our goal is to not have to do this ever again. Okay? So again, our inputs are going to be our x values, and our outputs are going to be our y values. However, we are dealing with a trig function here. And you all know with this, I'm starting with sine, and then we'll get to cosine. We all know that sine of any angle is equal to the y over the r value. And the angles that we preferred were either reference angles or quadrantal angles. And of all the reference angles and of all the quadrantal angles of those two groups, which ones did you like even better? Hopefully you said quadrantal angles. Because quadrantal angles, when we're talking about that on a circle, we know the 4, technically 5, 0, pi over 2, or 90, pi, or 180, 3 pi over 2, or 270, and then getting back to this 360 degrees, or 2 pi. So technically 5, because we can count this as 0 degrees and 360, or 0 radians and 2 pi. Those 5 points are very nice because we can just look at them and know if we had a choice, we're going to choose this to be a radius of 1, the unit circle we called it. So that would be the point 1, 0. This would be the point 0, 1, negative 1, 0, and 0, negative 1, which means if I know all of those, I know the x and the y for sure. And also, we should know the r value from the center of this going out in that direction. And that goes for any of these. That's a length of 1. That's a length of 1. 1, 1, and everywhere in between. The radius is a length of 1. So that means we know our x, y, and r. So all we're going to do is decide to use those 5 points. 1, 2, 3, 4, and 5 to get all the way around. So what I'm going to do is I'm going to cut this into these 4 quadrants. Quadrant 1, 2, 3, and 4. By labeling 1, 2, 3, and 4. And whether you put all of those in radian measurements or degree measurements, it's totally up to you. But remember, this is what we always called the x-axis, and this is what we always called the y-axis. And if you were to put 90 degrees, 180, 270, just increasing by 90 each time, all the way to get to their 360, one full circle, those are quite large numbers. And then we have to write the little degree symbol, and then we could also go the other direction, those 4 values. And that's fine. We can definitely do that, but those don't look like our typical x-axis that we've been drawing since day 1. Ours have typically looked like real numbers, like 1, 2, 3, 4 for each tick mark. Or we could do it by 2s or 10s or whatever we decide. So when you go to graph these on computer programs like Desmos or GeoGebra or even your graphing calculator, they're still going to look like this. They're not going to have the degree, 1 degree, 2, because then we'd have to have 90 tick marks just to get to our first quadrantal angle. So we're going to kind of think about this smart so that we don't have to work as hard. And we're going to decide to use radian measurements. Because when I put the first one there as 90 degrees in radians, pi over 2, what is that actually approximately equivalent to? Well, remember we said pi is a little more than 3, so we're just going to pretend it's 3. And if this pi right here is 3 divided by 2, that's about 3/2, which is about 1.5. So if this was worth 1, like I had originally, then I would have plotted that point right there, about 1.5. But since we get to make the x and y axes whatever we want, I'm just going to go ahead and put them where I want them. So the next one would be the next quadrantal angle, pi. So remember, it was increasing by 90 when we did it with degrees. Nothing's changed. It's still going to increase by 90 degrees, which is equivalent to pi over 2. So the way that I'm going to say this to you is, this is 1 pi over 2. This is 2 pi over 2's. But the 2's cancel out, so we just write that. And then the next one would therefore be another pi over 2, so 3 pi over 2, and then 4 pi over 2, which we can also simplify to put 2 pi. And I could also go to the left of 0, which, remember, the left would be the same values, just in the negative direction. So negative pi over 2, pi, 3 pi over 2, and 2 pi. So what we then need to know are what y and r are. And if you remember that we are on the unit circle, which means we chose a radius of 1, and therefore only need to focus for sine on the y values. So since we're starting at 0, we're going to go ahead and put our tick mark up at 1, and then -1, because we said that the 1 and the -1 were our maximums and minimums that sine would reach. So when we go to graph this, we're going to go ahead and start with our 0 radians or degrees, which our y value is therefore a 0. So our first value would be right there for sine at 0, 0. Now you can see why we started with sine. Next, we went all the way to the y value. Now, we could have done the 30, the 45, and the 60, because we also know those values. We know the sine of 30, 45, and 60. 30 was 1/2 right there. The 45 was √2 over 2, and then √3 over 2. All the way, as you see, increasing my y value to a maximum of 1 there. So my next biggest value at 90 degrees, or pi over 2, is going to go to 1. And all those other ones in between it. But then what does my y value start to do? It starts to, once we go further, my y value starts decreasing, getting smaller. Again, at that 60 would be √3 over 2. At the 45, √2 over 2. At the 30-degree reference angle in quadrant 2 would be 1/2. And I don't want to put those every time. I want to get there as fast as possible, so I know the next y value we're dealing with, it goes all the way back down to 0. Then it goes to that 3 pi over 2, down to a -1, because remember, all students take calculus. So they're going to be positive up in this quadrant, which, as you can see, if I start to build this, everything is positive. And then down here, it's going to be negative for all those reference angles. Again, the 30, the 45, the 60. We can build those and do it every single time, but it's not necessary. We knew all of those, and then it went down to that -1. And then as it increased, it would then get smaller and smaller, still negative, still below the y-axis, but smaller and smaller for my y value until it got back to 0. So smaller and smaller until it got back to 0. And so you can sit here and actually plug these values in, that 0 degrees or 0 radians, if you'd rather not put the degree symbol, pi over 2, pi, 3 pi over 2, and 2 pi. And we're just focusing on the y value, the output of this thing, which happens to be, it's a little confusing, the y over r ratio. And because the radius was a radius of 1, we said that we would just focus on the y value on our points. around this unit circle. Now, why did I stop at 2 pi? Why didn't I keep going? Well, what do we say is going to happen as we hit all these values, 360 degrees or 2 pi around? What would happen if I kept going? I would have just gotten the same values and therefore would have gotten that exact same curve continuously until we ran out of time on Earth. Okay, but what about the other direction? We could do the same thing and actually get all the negative values as well. But if we're at negative 2 pi, we're back at 0, 1, 0, negative 1, and 0. And you'll be able to see that exact same curve that we just plotted, but on the negative side. So we're going to talk about that and the period of time that it takes for this thing to repeat. We're going to talk about the maximums and minimums, the amplitude, kind of like the altitude of an airplane, right? How high up or down this thing went. And all those things we're going to start naming. But before we do, let's do the exact same thing, but now with cosine. All right, so again, we could go ahead and start by drawing out our circle and doing that, or talk about the input being our angle, x, and our output being that value, y. Now we know that cosine of any angle is always equal to x over r, the adjacent over hypotenuse. And if we're dealing with our unit circle again, then we already know these points, which we call the quadrantal angles. So again, going for all 4 of those quadrants in either the positive or negative direction. But this time, knowing that our radius is going to be a 1 because we're on the unit circle everywhere, we can just focus on x. And if we're only looking at the x this time, then remember, for every one of these, when we go pi over 2, pi, 3 pi over 2, and 2 pi in either direction, we're only focusing on the x value of all of those, technically 5 points, even though you only see 4, because we're counting 0 and 2 pi as being the same point. All right, so focusing on the x's, that means at 0 degrees or 0 radians, we're going to be up at an x value of 1. That's how far out we would be. Then as we rotate the 30, the 45, and the 60, we could do the same thing, but notice our x values are actually starting at 1, and then they're getting smaller, our x values are. Getting closer to that 0 that we started at, until we get to 0 at what angle measurement, what input value. And again, that would be the pi over 2 or 90 degrees. So we'd start at 1, we go to 0, then our x value goes to negative 1. Kind of looks the same as the sine, doesn't it? And then 3 pi over 2 goes to 0. And then we are back at our 1 once we get all the way around. Now again, we could do everything in between the 30, the 45, and the 60, which would be the cosine of 30 is root 3 over 2, 45, root 2 over 2, and 1/2. And so we get a little something like this. And we connect all those values. And don't forget, not only would we have that to the right, we would also have the 1, 0, negative 1, 0, and 1 if we graphed it to the left, the negative direction, starting downwards. All right, so again, hopefully you can kind of see why these things are called the sine curve or the cosine curve. And if you wanted to do the t-chart and plug in those values for x, the input, the angle, use the quadrantal angles and only those to get the 5 key points. And again, these two technically are the same, are starting an end point where we would then start another one going in that same form as we've seen here twice. So if you want to start by getting comfortable by plotting points like we did with our lines way back when, we're looking though to try to do this as quickly as possible. And this is therefore that way, that technique. Because you know that they're not going to just give us regular old sine or regular old cosine. They're going to start adding numbers and variations in there. And so we're going to have to start looking at all the attributes of these things, which I'm going to give you a little bit more notes right now. And then we'll go ahead and continue on with some additional pieces to the sine and cosine functions to see what will change on their graphs. Okay? But the key is that you know we are dealing with this graph for cosine and this graph for sine. If you can start with those and get those quickly, then we're going to just make a few adjustments to this equation and that equation in order to manipulate these. All right, so here comes some more notes, and then we'll get right back into adding on some pieces to translate these parent functions, we're going to call them, sine and cosine, to stretch a little bit differently. So here's the first thing. I wanted to give you it all in one nice graph here, one place. And again, you can see that our sine starts at 0, goes to 1, 0, -1, and then back to 0, where our cosine starts at 1, then 0, -1, 0, and 1. And you guys remember the all students take calculus way that we broke this up to see where things are positive and where things are negative? Remember that was done by our quadrants? Well, if I broke this into our 4 quadrants, here's quadrant 1, 2, 3, and 4. So we have all students take calculus. And you can see that everything is positive here. It's all above the x-axis. Everything is positive here above the x-axis, even though it's getting smaller. And then, since those are for sine, these would be negative below the x-axis. Right? And again, same thing over here for cosine if you wanted to. All students take calculus. And so you can see positive, negative, negative, and positive. Right? So a lot of the stuff that we dealt with before, again, if you want to make a whole t-chart to find these values to get more points, so be it. I'd rather you be able to get there a whole lot quicker. So remember we talked about both sine and cosine being either y over r for any angle, or for cosine x over r. And because the r is always going to be some number, then that means it can never equal 0. Which means we will always get something out no matter what angle you choose. There will never be any issues. And you can probably guess what the other 4 trig functions, they don't have r's in the denominator. We will have issues. There will be zeros in the denominator, which will make our graphs a whole lot more difficult. Okay? But that's why they say that it is continuous and the domain is from negative infinity to positive infinity. This would just keep going in this form forever. Same thing with cosine. Right? So that's nice. The domains are from negative to positive infinity, meaning we don't have any issues. The rest of this stuff, the only thing that I really want you to kind of grasp from it, you can definitely read through it, but you need to know that the period is 2 pi. And the period is what they call the length of time or period of time that it takes to repeat. And again, hopefully you can see that right up here. When we look at the graph of this, from negative 2 pi to 0, you can see there's that curve. And if I did it again, from 0 to 2 pi, I'd have that exact same curve. And the same thing for cosine. From 0 to 2 pi, that's when I would start repeating. And remember, the reason for that is when we're dealing with the circle, when we start at 0 and get all of those other quadrantal angles, we will make one full circle, and then we would get all the same values if we did it again and again and again. So that's why it takes 2 pi or 360 degrees to repeat. Now you can also talk about symmetry with these because they are symmetrical. Cosine's a little bit easier because, as you can see, if I drew a line right here, it looks like if I folded it along that line, the left and the right, there'd be no overlapping. Okay, they'd land perfectly on one another. Where if I try to do that here, that doesn't work because this point would map right over here, and that's no good. All right, so with this, there's actually still symmetry, but it's about the origin, it's called. And so we call those things odd functions when it's about the origin, and even functions when it's about the y-axis. All right, and the way that we find those is by simply plugging in a negative x and seeing if we get the original thing back out. If you get the original by putting in a negative, then that means it's even. You'll get the same thing. Whether you're over here on the left side, you get that value, or the right side, you get that same value. But if you notice over here, when we plug in, say, like negative pi or pi, we end up getting the opposite value out. And so that's why those are called odd functions, right? Because you get the opposite. This one maps here and this one maps here. They're opposites. Where over here, cosine, you get the same values out. So they're even. Think about scoring. Score is even, they're the same. If it's odd, then we're going to think about opposite. Okay? So a lot going on here. If you want to grab a picture of that before I cluttered it, then go ahead and rewind it and grab a nice little photo for you or a screenshot, because there's a little bit more with the even and odd stuff if you guys wanted to check that out. Okay, the even and odd is a little bit more explained right here. But we also talked about how it increases from one to another, okay, for sine and cosine. And again, that's because we're looking at the y value for sine and the x value for cosine. All right, so if that helps you to remember how to graph this thing, great. If not, just keep working at it, memorize it. I know it's another thing to memorize in this class, but trust me, it's going to be worth it. Because if you can do these, then you're probably thinking, well, I know two that are really similar to sine and cosine. They're reciprocal functions, cosecant and secant. If you know these, then it'll be a whole lot easier when we're trying to do cosecant and secant. We'll get to tangent and cotangent, but give yourself some time working with these first. So although those are some of the attributes that we definitely wanted to look at, and namely what we call parent graphs of each of those, we again want to be able to graph these as quickly as possible when they don't just give us the parent graphs of sine and cosine by themselves. So what if there's a number multiplied in front of either sine or cosine? What effect do you think that will have? And the way that I look at it is, you know what? It's not being done to the x, my input, my angle. So I would still evaluate the cosine or sine of 30, 45, 60, or all the 90 quadrantal angles. So then what is it going to affect? Because it's got to have some effect to my graph. Otherwise, why would they even put it there? Why would we be talking about it? And since it's not being done to the x, my input, my angle, then it is going to affect the y values for each of these. And remember, the y values were that up and down vertical line. And because it's what is called the amplitude, you can think of it as the altitude. How high up or down does my graph actually go, right? It's kind of like a stretch. We call it a vertical stretching. And it does not matter if it's negative. What we're really looking for, the absolute value of that, is what is the actual length that we're going to be going and stretching from the x-axis. Now you may be wondering, well, can we only stretch it up and down longer, or can we shrink it down? Well, you're absolutely right. We can also shrink, but it's not when it's negative like you'd think. So since 1 is the thing that we used for just regular old sine and cosine, then anything greater than that is going to make it bigger. So then what would shrink it down and make it smaller? Anything less than that. But as you can see, it also has to be greater than 0. My a has to be greater than 0. So again, we're only looking at the value of it. We'll talk about when it's negative and what effect that also has when we get into this a little bit deeper. Okay? The other thing that we're going to talk about, which I've already mentioned, is the period. And the period of time it takes for our graph to repeat. And we said it was always 1 full circle, 2 pi, all the way around. Because for that to repeat, we'd hit all these values for both x cosine or y sine, but then when we hit here, we would just start repeating them. So 1 full circle all the way around would be when we start repeating. And because we hadn't talked about the x values having changed to them yet, you can see here, now we will have something being done to the x. And so obviously it's going to affect our x-axis when we go to graph. Where up there, it was the y-axis. So if it's being done to the y, it's going to affect the y-axis. If it's being done to the x, it's going to affect the x-axis. And if you're thinking about x's, I'm sorry, that's not a good place to be. All right? Now, I'll make that little joke because that's how I want to remind you of what to do when you see these things. All right? When it's multiplied by some number up there and it's not being done to the x, then that means it's being done to the y's. And if it's y's, then you should listen to it. Do exactly what it says. But if it's being done to the x's, remember x's are x's because they wanted the opposite of us. And so therefore, you're going to do the opposite of what we normally would have done in the x values. And remember, that was 1 full circle all the way around for our x-axis. We did the 1, 2, 3, 4 quarters all the way from 0 to 2 pi. That was what we call the period. And because it's now being multiplied by something, we will take our normal period of 2 pi and we will divide, since it's multiplying, by whatever b is. And that will then change all of our 4 quarters and the period or length of time that it takes for this thing to repeat. Okay? So again, you can think of this as horizontal stretching or horizontal shrinking. But notice that this is different. B is greater than 1, then we are shrinking. See, it's the opposite for x's. Again, my little joke, that's why they're x's. Okay? Between 0 and 1, some fraction, then we will be stretching it. It has the opposite effect. Okay, so that'll make more sense when we actually do an example, so hang in there. I wanted to give you the notes before we actually started doing some first, and then we'll do a few examples to hopefully cement it down before you try it on your own. At least feel a little bit more confident going into it. So before we do our examples with these additional parts to our parent functions of sine and cosine, I wanted to give you the whole picture here of all the things that we've talked about and even some steps. I don't necessarily have to do this in this order, but this is a nice little thing to at least start with until you get the hang of it. All right? So read through this, but when we're dealing with any sine function or cosine function, whether they have that A amplitude or that B that's going to affect our period, we need to figure out, first off, what trig function we're dealing with. Is it sine or cosine? So we know what it looks like. Then we'll find the period by taking our original 2 pi, and since it's multiplying, we'll divide by b. Right? Then we'll take those and we will cut it into those 4 quarters that we normally would have on our x and y axis of our unit circle. I will call these our quarters for that reason. We're going to cut it into 4 equal parts. Then, I know it's deceiving when we say 4, but remember there was actually 5 points to get all the way around our circle. So now we're going to take those and find those 5 x values. I'll just call them the 5 key points. All right. And we need to know which ones are the maxes, the mins, the intercepts where it crosses through our x-axis. All of that information depends on whether it's sine or cosine. All right. And then lastly, we just have to plot them. Plot those points and figure out which sinusoidal curve that we have with that certain amplitude with our new period. All right. And when we draw it, just make sure you pay attention. Do they want additional periods or do they just want one period? Hopefully just one, then you don't have to go to the left or even further to the right. Okay, so this should be a nice little way to at least start it. If you don't want to do that, that's all good. I'm not going to usually go now step 1, then 2, then 3. I'm just going to graph it. And remember, our goal is to be able to graph these as fast as we can now graph lines.